Good day everyone. We are the Group 5 and today's presentation we are presenting about the apportionment paradox. This presentation will include the introduction, description, definition of terms, steps and procedures, sample problem, solution, interpretation or answer, and the conclusion.
Apportionment involves dividing something up just like fair division. In fair division, we are dividing objects among people, while in apportionment, we are dividing people among places. In history, apportionment is used every day in American politics. It is used to determine the size of voting districts and to determine the number of representatives from each state in the US. House of Representatives. Overall, apportionment used to divide up resources in as fastest way as possible. The paradoxes emerged as mathematicians and political scientists realized that no single method for apportionment could completely avoid unintended or counterintuitive outcomes when translating population data into seats. As a result, these paradoxes became important in highlighting flaws in the methods for fair distribution. A paradox is a statement or situation that contradicts intuition or expected outcomes, exposing flaws or limitation in reasoning or models. Apportionment is the process of fairly distributing fixed resources, often seen in elections and resource allocation. Apportionment method is a method of rounding real numbers to natural numbers, while paradoxes in apportionment can arise when rounding techniques are used to assign whole numbers based on proportional values. Alabama paradox. Alabama paradox, an increase in the number of available items causes a group to lose an item, even though population remain the same. Population paradox. Population paradox. Group A can lose an item to Group B, even when the rate of growth of the population of Group A is greater than Group B. New state paradox. New state paradox. The addition of a new group with a corresponding increase in the number of available items can cause a change.
Definition of terms. So what is apportionment paradox? The apportionment paradox happens when the method of dividing seats or representation among different groups leads to results that seem unfair or unexpected, even if the rules are followed correctly. In simple terms, it's when a group ends up losing or gaining seats in a way that feels illogical, even though no mistakes were made in the calculation. This usually occurs because of the mathematical rules behind apportionment methods.
And here are the steps and procedures of each paradox. The first paradox is the Alabama paradox. Step 1 of the Alabama paradox is list each state's population. Step 2, choose a total number of seats in the House. Step 3, compute the standard divisor. Step 4, find each state's quota. Step 5, assign each state its lower quota. Step 6, determine leftover seats by subtracting the sum of lower quotas from the total seats. Step 7, distribute leftover seats to the states with the largest fractional remainders of their quotas. Step 8, record the seat distribution for the total number of seats. Step 9, increase the total number of seats by 1 or more. Step 10, repeat steps 3 to 8 to get the new seat distribution. Step 11, compare the two distributions. If any state has fewer seats after the increase, the Alabama paradox has occurred. The next paradox is the population paradox. Here are the steps and procedures of the population paradox. Step 1 of the population paradox is list each state's population at time Step 2. Choose the total number of seats in the House. Step 3. Apply Hamilton's method. Compute the standard divisor, find each state's quota, assign lower quotas, distribute leftover seats by largest remainders, record the apportionment. Step 4. Update populations at time 2. Some states' populations will grow at different rates. Step 5. Keep the same total numbers of seats in the House. Step 6. Reapply Hamilton's method with the new populations. Step 7. Compare the two seat distributions before and after population changes. Step 8. Check for paradox. If a state with a faster population growth rate ends up losing a seat to a state with a slower growth rate, the population paradox has occurred. Next of the steps and procedures of the different paradox is the new states paradox. Here are the steps and procedures of the new states paradox. Step 1 of the new state paradox is list populations of the existing states. Number 2. Choose the total number of seats in the House. Step 3. Apply Hamilton's method. Compute the standard divisor, find each state's quota, assign lower quotas, distribute leftover seats to the largest remainders, record the seat distribution for the existing states. Step 4 of the new states paradox is introduce a new state with its population. Step 5. Increase the total number of seats in the House to give the new state at least one seat. Step 6. Reapply Hamilton's method using the updated populations and total seats. Step 7 of the new states paradox is record the new seat distribution. Step 8. Compare the old and new distributions for the original states. Step 9. Check for the paradox. If any of the existing states lose or gain seats in a way unrelated to the new states addition, the new states paradox has occurred. These are the steps and procedures of the new state paradox.
Good day everyone. Today I'll report about sample problem 5. This problem is about how scholarship slots are distributed and how it shows the population paradox. So first, let's look the initial occasion. The university assigned 60 scholarship slots to 3 colleges. Based on their population, College of Education had 1,500 students and it got 17 slots. Next is College of Science had 2,100 students and it got 24 slots. So College of Engineering had 1,800 students and it got 19 slots. The total was 5,400 students and exactly 60 slots. This was the first fair distribution. A few months later, the student population changed. So education increased by 300 from 1,000 to 1,800. Science also increased by 300 from 2,100 to 2,400. Engineering stayed the same at 1,800. The new total becomes 6,000 students. Now, let's reassign the 60 slots based on these new numbers. Education with 1,800 students should get 18 slots, but it stayed at 17 slots. And science with 2,400 students should get 24 slots. but it increased to 25 slots. So next is engineering with 1,800 students should get 18 slot, but it went down from 19 to 18 slot. From this new distribution, we can see their important things. Number one is education gained 300 students, but it did not gain a slot. Second is engineering did not lose student, but it lost one slot. The third one science gained 300 students, and it also gained one slot. Now the question is, why did engineering lose a slot even if number of students did not decrease? The reason is because allocation is based on the proportion. Since education and the science both increased, the share of engineering became smaller, so one slot was taken away from engineering. And this led us to the population paradox. The paradox happened when a college gains students but does not gain slot. Another college stay the same but lose slot. Meanwhile, another college gain both student and slot. In our case, education gained 300 students but no slot. Engineering stayed the same but lost one slot. And science gained both student and slot. That is the population paradox. In conclusion, after relocation, education has 17 slots, science has 25 slots, and engineering has 18 slots. So this example clearly show how the population paradox work in a real situation.
Welcome everyone, I'll be presenting the solution. So let's dive into the scenario to fully understand the given situation. So there are three colleges, which are the College of Education, Sciences, and Engineering. So let's say that the school needs students for their scholarship or slots for their scholarship. So first, let's identify the percentage of each department of college to get the initial assigned total, and it's just simply divide the total population of the students in all colleges, which is the total of 5,400, with each department of college. First, the College of Education has its 1,500 students, will divided by into the total population of 5,400 and times 100 is equal to 27.78. And next is the College of Science. It has the 2,100 population of students as divided to 5,400 and times 100 is equals to 38.89%. For the College of Engineering, it has a 1,800 divided by 500 and 5,400 times 100 is equals to 33.33%. By this percentage, we will able to identify the initial slots assigned in each college. So we are able to identify. So for the College of Education, it has a 17, and College of Science will have a 24 slots, and the College of Engineering has its 19 slots. So the total of this is 60. A few months later, students' number change. We have to redistribute the slot. For the College of Education, it increases to 1,800 students, adding 300 of it. College of Science increases to 2,400 students, adding also 300. For the Engineering College stays at 1,800 students with a new total of 6,000 students. Let's calculate the new quota and the updated sets of numbers. For us to be able to get the new quota, here's the computation. Compute the total population and the slot given, so which is 60, and the total population is 6,000. So 6,000 divided by 60 is equals to 100. So let's use the 100 to calculate the quota, the new quota of each college. So for education, 1,800 divided by 100 is equals to 18. So for sciences, 2,400 divided by 100 is equals to 24. For
Now
engineering,
we have reached the end of our
1,800
presentation.
divided by 100 is equals 18. So with a total of 60. Here's the new assigned slot of each college department. For the College of Education, from 17 to 17, which means no gain. So for the College of Sciences, from 24 to 25, it means that it increases by 1. And then for the College of Engineering, from 19 to 18, decreased by 1. And that's all for the solution.
Looking at the reallocation, it feels unfair at first glance, diba? Education added 300 more students yet didn't gain an extra slot, while science also added 300 but managed to get one. Then there's engineering, which didn't lose any students but somehow ended up losing a slot. It shows us that the way seats or slots are divided isn't always as straightforward isn't as just adding numbers. This outcome is what we call the population paradox. It happens when a group grows but doesn't benefit, or when another group that stays the same ends up losing. In this case, education's growth wasn't enough to push its quota past a whole number, so it stayed at 18 slots.
So science growth, however, pushed its quota up enough to round higher, so it gained a slot. Engineering didn't shrink at all, but it lost a slot because of how the adjustment shifted overall. What this really tells us is that numbers don't always behave the way we expect them to. Even if the math is correct, the results can feel unfair or illogical. The paradox reminds us that no apportionment method is perfect. Sometimes the distribution depends on rounding, and that can create outcomes that don't seem to match the effort or growth of each group.
Now we have reached the end of our presentation. In conclusion, the apportionment paradox highlights the limits of fairness in distributing seats because seats are whole numbers. Small changes in population or total seats can lead to surprising results, such as states of losing seats despite growth or gaining seats when others shrink. In short, every apportionment method faces trade-offs, and no system completely avoids unexpected outcomes.